Hello everyone, thank you for having us here. Our subject is more related to an operational need. So, my name is Mohamed, my colleague Anh-Tuan, and today we will present our web application for mechanical integrity evaluation of buried pipeline under surface overload. To do so, I will give a quick overview of Natran and its infrastructure, a quick state-of-the-art of the mechanical integrity assessment as it is managed at Natran. And after that, we will move to the finite element application based on Codester with a live demo. And after that, we will conclude and we'll give some hints about the future work that will be done. So Natran, maybe you're more familiar with the previous name, GRT Gas. We changed, the company changed its name since the beginning of last year, moving from GRT Gas to Natran. And we are transport company using pipeline at high pressure in France and in some countries of Europe. The group consists of 3,800 employees with 33,000 kilometers of pipeline. Me and my colleague are part of the R&I Center for Natran, the Research and Innovation Center, which consists of 120 people spread across 4 departments. And we are part of the pipeline integrity department, working on pipeline integrity, on metallic and non-metallic pipeline integrity. We are located in Villeneuve-la-Garenne, but we have three different technical sites here in Ile-de-France. After to the mechanical integrity assessment, how it's managed at Natran, to give some context before moving to the finite element application. Some key numbers. In 2026, we have 6,000 kilometers of pipeline that will be inspected. So there is inline inspection that leads to large batches of defects that come in with the inline inspection. Each year, every year, we have 4,000 external interferences and third-party work requests that we have to process. And the typical scenarios and the typical requests are always or often the surface load requests. So the surface load can come from road traffic, construction equipment, embankments while creating new roads, as we can see here, settlements of the soil. And of course, there is a lot of other requests linked to vibration or soil compaction, dynamic compaction that we have to assess. Due to those numbers, to this large number of requests, it is important to create, to develop tools, and this is why we have at Natran two level 1 tools for calculation, and we have for sound for healthy pipelines Ramses, which assess the loadings, the external loadings to the pipeline, and we have also guideline, which stands to guide d'analyse de défaut for the pipelines which contains defects. For Ramses, as you can see, it has many modules that respond to a lot of operational issues like overload, vibration, lifting of the pipes, slow pipeline in slopes, and so on. It's more than 1,000 calculations done per year, and it's easy to use. It's really intuitive, and now we have many companies that have the tool Ramses and use it for their own purpose. In the other side, for all the defect that we find after the inline inspection, we have guidelines that take the data directly from coming from the inline inspection and assess the defect based on their characteristics. So it's like 2,000 to 3,000 defects that are analyzed directly. With guideline. Some of the overload configurations, some of these defects, some of configurations are outside the applicability of this level 1 calculations, or they are simply not acceptable using these standards applications. And this is where we use the finite element analysis to do more detailed analysis. As we can see, there is a lot of configurations where we have a repartition slab between the soil surface and the pipeline, and we don't have the level 1 tools that can make those calculations. Also, we have the problem of interaction between multiple defects and different loading conditions that are combined. This is why we had this is where at Natran RNI we have those requests of doing finite element analysis to answer those type of questions. It's a lot. As you can see, it is large numbers, and we have a lot of requests of this kind. This is why we had the idea of creating also an application. You will see that we had the idea of developing an application for those external loads, and also an application for the defect analysis, but this time not based on standards, but based on Codaster calculations.
Hello, my name is Anh-Tuan. I will show you simulation tool at Natran that are built with Codaster. For complex overload case that cannot be handled with simple analytical model in Ramses platform, a desktop tool was developed at Natran NI using Salomika. This tool model steel and polymer pipeline under different overloads, and soil model elastic and modular. The calculation and processing are fully automated. However, a desktop tool has several limitations. This slide explains why we decided to move from the local application to web platform, which automate both calculation and processing, while avoiding licensing constraint, maintenance issue, security risks, and performance limitation. The application is deployed on Linux server hosted by Icola. The monthly operation cost is 18,000. This slide shows the pipeline of application. A web client sends request to a cloud backend built with Fast API. Fast API is a framework Python. The server runs the Python and Salomika. Then the return result to web client. This approach enables scale-up cloud computing and a clear separation between the user interface and numerical simulation tool. I will show you demonstration of application. Accessible via a standard web browser. First, I show the material and parameter.
This is the interface, the intuitive interface that we made, where you can choose the material type, the outside diameter, and the characteristic of the pipeline.
For information of the parameters, you can click have width dimension. They are for overload case. In this case, I show the point overload and embankment. Is a name project it requires. Then I connect to server Linux to show the simulation process. As you can see, then I start calculation. The web browser send request to server. Server runs open the new terminal for run calculation. As you can see, the process of you can see the status of project. In this case, it's pending.
The calculations takes 2 to 3 minutes. So as you can see, in the
server, for the name week, name of project is created. As you can see, the input data from JSON sent from the web browser. Finally, the calculation is finally. As you can see, the state value depending on internal pressure. In this case, in this case, overload is acceptable. And the server in opens a new terminal for processing. As you can check the status of reports, and you can download the reports. In the reports, there's some information of a mesh, photo of mesh, and few of state and few of the displacement, and input data and result.
Everything is automatically generated.
And you can download the mesh and view it in Kitware Glen, in Kitware Glen.
In order, we choose this method in order to get the user and let him have everything online without any other installation on his local desktop. So as a conclusion, we can say that the developed application significantly reduces the time required to perform those type of calculation compared to the manual finite element workflow. The interface is intuitive, so engineers without FAA expertise can run advanced simulations. In addition, we also have all the benefits of a web application. So centralized management, secure access, and so on. For future work, I think you understood maybe the main goal. It's to deploy this application within the engineering department to let them do their own calculations. Once, of course, validated and the qualifications are completed. We also want to integrate this application API into Ramses to extend the levels of calculations, maybe for also the external clients. It's still in discussion, so we will see. And like as I told you in the beginning, I was talking also about the defect analysis. So one of the works that we are carrying out as well is to adopt this approach to develop also an application for defect analysis using Codaster. A quick example: the work is in progress. We already have the scripting. I don't think we will make a Tkinter interface for this application, but now we have the workflow of developing a web application. So we will move directly to a web application that is similar to this one, where it will be used to defect analysis. We already done the 3D mapping of the corrosion that can automatically put into the mesh. The nodes will automatically move using the 3D mapping of the defect and launches the calculations and giving back the result, and the processing also automated. So there is the interface to make, we have to validate all those kind of calculations. Thank you, everyone, for your attention.
Just a question about the web app. Is it multi-users? So more than one user can use it?
Is it, pardon?
For a multi-user, for a lot of users?
Yes, of course.
And
yes.
So how do you handle, for example, in the backend, so if there are two analyses, it will take it, but if there are more, let's say, is there some kind of balancing?
Traffic?
For now, it's not, yeah.
When we have a lot of users at the same time?
Yeah,
or,
the question, if you have done anything on this, yeah.
That is working for many users.
And is going to wait
because in the server one user have a folder.
Okay.
For saving the data.
All right. Thank you.
We already trying this application, so we are like 5 or 6 users. We did the test by making calculation at the same time. For the moment, it's a beta test server. It's only for testing the application. For the moment, it's working, but of course, for if we have to deploy the application within the engineering team, we will go through those questions of traffic of a lot of users and see if there is something that we have to change in the architecture of this application.
Yeah.
But for the moment, it's working. It's working for our team. So we are not computer science engineers. So we are trying to develop this app. The backend is our work, but for those type of issues, I think we will have to ask for help.
Sounds great.
Which tool do you use to generate the mesh? You use only SMesh and Shaper, or something else?
Salome.
Salomika.
Salome Meka.
Thank you.
And we don't need use interface. Use terminal.
Okay.